Today we are going to look into some properties of functions. So let's start with this ones right here. Increasing and decreasing properties. What makes a function increasing and what makes it decreasing? At this point, some of you may think, what is there to talk about? What is there to think about? Increasing and decreasing should be very easy and straightforward to determine. Increasing function is just a graph that simply goes up. Okay, all of a sudden you associate the word increasing with going up. That is the idea, so let's write that down. Increasing means something must be going up. So goes up. At this point, we don't know yet what goes up. And for decreasing functions, something must be going down, the opposite. So here, something goes down. It should be a graph that appears to be moving down. Okay, well, this kind of thinking and definition is okay, but not entirely correct. This is actually ambiguous, and you can make a mistake out of this kind of thinking later, and here's why. Let me give you an illustration on the right-hand side. So let's have some axes. Okay, y-axis and x-axis. Y and x. Here, I'm going to explain to you why you can't just associate increasing with going up directly and decreasing with going down directly. It can be confusing. And let's see here. Here's why. So, the next thing I'm going to give to you is a line, okay? A graph right here, black one, very simple, straight line. And the next question is this line I gave to you, this black line, a function? Okay? And in order to answer this, you have to think of the definition you learned from the last lecture, the definition of a function. And if you can recall, a function is a transformation where one input can only create one output. That is the only definition we need here. And in this case, we know that input is x and output is y. So we need to check if each x creates only one value of y along this line. And as you can see here, all the way through, starting from here, one value of x only has one value of y associated with it, which means that in this case, one input creates only one output. And you can answer with confidence. This line right here is definitely a function. Okay, let's call it fx. You can call it something else like gx or hx. Okay, we have the function right here. Now, the next question to you is this function fx increasing or decreasing? Okay, increasing or decreasing? That is the question. At this point, I think 9 out of 10 of you would say that this graph right here, this function is increasing. And I ask you why, and you would explain to me that if we pick a point, maybe somewhere around the middle, if we pick a point right here and we observe this point, we can see that this graph is actually going up. 9 out of 10 of you would see this graph as going up in this direction. Okay. According to you, this is going up, and along this direction, function value and the y value increase. So you conclude that this is going up and everything increase, so this is definitely an increasing function. Okay? And the idea is you see it as going up, 9 out of 10. But it turns out that we have one person left. And that person, he or she says that I don't agree with you guys. I don't see it as going up. And he or she continues that the reason that you guys sees this function, this line as going up, because you guys choose to look at this graph to the right hand side. You guys have this direction in your mind to look in this way. That's why you see it as going up. You look to the right. But that person, that one person, says that he or she is different. He or she wants to look at this graph to the left hand side. I want to look at this graph in this direction. Okay. Can that person do that? Of course, because I haven't told you whether you have to look at this graph to the right or to the left. So you can look at this graph the way you want. And this person choose to look at this graph to the left. And along this left direction, we can see that this same graph appears to go down along this direction. Same graph, but now it goes down. Okay, down, and along this direction, the function value and the y value decrease, which means that he or she concludes that this function should be called decreasing, because looking to the left, this is decreasing. All right, decreasing. And as you can see here, it depends on how you look at the graph, not the graph itself. Okay, whether it's going up or going down. Looking to the right, this same graph goes up, but looking to the left, this same graph going down. So what's important here is that when it comes to increasing or decreasing properties, you can't just say that it goes up or goes down. You need to specify the direction you are looking at the graph. So make a note right here. You need a reference when it comes to looking at the graph and determine whether it's going up or down. Very important, reference. And it was missing. So when it comes to determining the properties of increasing and decreasing of a function, you need to specify the direction you are looking at the graph, and that direction is to the right hand side. So let's include it right here. When it comes to determining the property of increasing or decreasing, you have to look at your graph, at your function, to the right hand side. Look to the right hand side, or in other words, you are looking at the positive infinity of x variable. Positive infinity of x. So to conclude this, it is not just about the shape of the graph, it's about how you look at the graph too. And for this properties, you have to look at the graph to the right. So let's highlight this. You need to keep in mind that we are going to keep this only for the increasing and decreasing property. You have to look at the right. This one is not an option. Okay. Now, if I ask the same question, but I put a condition here. Looking at this graph, and you have to look at this graph to the right. Is this function going up or going down? And if I have this condition to force you to look to the right, you are going to say that this graph is going up 10 out of 10. Okay, so now it's clear. We have to specify the way you look at the graph, and that has to be the positive infinity of x variable. Okay, a little bit confusing, but if you think about it, it matters how you determine this property. You have to look at it at the right way. Okay, now we have this definition right here, and it's not clear enough. We are going to complete this to make this more clear. So when it comes to increasing, let's start with this one. Increasing property of a function. Increasing property. What goes up? We are talking about function value has to go up, has to increase. So fx has to go up, okay? Along what direction? The direction on the right. But here I'm going to make an adjustment when it comes to wording. So function value goes up when x increases. Okay, what does it mean when x increases? When x increases, it means that we are moving along this direction. All right, x increases. So same as to the right and to the positive infinity. So you can make a note right here that when x increases, it's the same meaning as looking at the positive infinity of x, or look to right, same thing. Okay, now let's do the same for the decreasing function. The definition up here, decreasing, it means that the function value fx has to go down. And now we specify the direction that we look at the function. When x increases, same direction, to the right, to the positive infinity. Okay, once again, make a note right here. When x increases, same meaning as positive infinity and to the right. So from now on, it's going to be this, to the right, to determine this property. All right, now we have the definition of increasing and decreasing functions. And now it's correct. But the next job that we need to do is to translate this into mathematical terms. We can't leave it as sentences right here. So let's start with this one. Let's start with the increasing function. So first of all, I'm going to translate this when x increases into some mathematical terms. Okay, so I'm going to either change it to an equation or inequalities. So let's take a look here. So first of all, let me take this out since we already know about this. Okay, to the right. Okay, I'm going to translate this when x increases into some inequality. So let's take a look here. So I'm going to specify 2 points on x-axis, x1 right here and x2 right here. Okay. Now this, when x increases, I'm going to change it to if x2 is greater than x1. All right. This is we are talking about x2 is larger than x1, so x is increasing. Then the function value goes up. Then function value at x2 must be larger than function value at x1. There you go. We translate this into this inequalities. If x2 is greater than x1, then function value at x2 must be greater than function value at x1. So there you go. Now that is the definition that we translate directly. But when it comes to this definition of increasing, it turns out that we have an exception here. We have this equal sign. So it means that it's okay to stay still at some point, but you can't decrease. You can only stay still or going up, right? So this is important. This is greater than or equal to. So let's put a box around this definition. Okay. So there you go. This is the properties, mathematical properties of increasing functions. Sometimes we call this non-decreasing. Non-decreasing. Okay, because we have this equal sign right here, which means that sometimes you can go up, and at some point you can stay still and go up again. It's kind of hard to draw. I'm sorry. All right, you have to go up, and at some point you are okay. It's okay to stay still, and you can go up again. This is considered to be increasing function. So even though right here seems to be staying still, it's okay. All right, so that is the definition of increasing function. Now, there is a difference between increasing function and strictly increasing function. So right here, strictly increasing function, everything is similar except that this one is a little bit stronger, strictly. So let's take a look at the difference here. Same thing, we have the same direction. If x2 greater than x1, looking to the right, the function value at x2 must be greater than. So this one must be greater, okay, than the function value at x1. So there you go. Main difference between increasing and strictly increasing is the way that strictly increasing is stronger. And it means that function value must be increasing at every step. At every step. So there is no this exception right here. So it has to be keep going up all the way through. Okay, now that is the definition for increasing and strictly increasing. Now we move to decreasing and strictly decreasing, and as you expect, it's going to be similar. So let's take a look here. So now this one is about decreasing function. And once again, we keep the direction the same. We are going to look to the right. If x2 greater than x1, we are looking to the right hand side. Now, function has to be lower, decreasing. So the function value at x2 must be less than function value of x1. Okay, sorry about that. Function value of x1. But since this is just decreasing, not strictly, so we have this equal sign right here. Less than or equal to. So your graph can appear to be something like this. Going down, and stay still. And going down. This is still considered as decreasing function. Okay? Right. So this one, you can call it non-increasing. Non-increasing. Alright, now last one. Stronger version than the decreasing definition. So we are going to have this same direction of looking. x2 greater than x1 looking to the right. And now the function value has to be strictly less than at x2 must be strictly less than function value at x1. So there you go. Okay. And as you know, this one is stronger than the definition for decreasing function. And that is the all you need to know about the definitions and about the properties of increasing and decreasing. It's not just about going up. You need to know which direction you are looking at your function, and it has to be to the right. Okay? Now, let's move to the next properties, and that is the properties of being even and odd. So, even and odd property of a function is actually all about the symmetry of the function curve itself across the axis. So let's take a note on this one. It's all about the symmetry. Characteristic of the function curve. So it's going to be related to the shape of the curve, of function curve across axis. And we are talking about both axes here. This one, both x and y axis. So the keywords, even and odd functions, it's all about the symmetry. Symmetry across axis. So we are going to do some flipping of the graph across both x and y axis. So let's check it out here. Let's start with the even function. Let's check on the conditions that can make a function even. So let's take a look at this one right here. Now, fx is even when? So let's take a look at the condition right here at the end. When function curve, once again, it's all about the shape of the curve. So when function curve, okay, function curve is symmetric across y-axis. Symmetric across y-axis. In other words, function curve, shape of the curve, shape of curve is mirrored horizontally across y-axis. Is mirrored horizontally across y-axis. same thing. You can think of this as symmetric across y-axis, or it's mirrored across y-axis. So let's take a look at some examples of even functions. So let's take a look at this one right here. Function fx equal to x squared. So let's try to plot this function on a graph. I'm going to do it down here. Okay, let's have y-axis and x-axis. And since this is x squared, it's going to be a parabola, simple one. Okay, something like that. And going up, doesn't look good, so let me fix on this one. Okay, a little bit better. So this is fx equal to x squared. Now let's check the symmetry across y-axis. To check that, we are going to consider y-axis as a mirror. So let's imagine that this y-axis is a mirror, and we are going to see whether the left-hand side and the right-hand side looks like a flipped version of each other or not. So as you can see here, if you try to flip this curve on the right-hand side of the y-axis to the other side, you are going to get the exact same thing. And that's why I say that it's the mirrored version horizontally of each other. So here, symmetric. So from this I know that I flip once, I get the symmetry. So this is symmetric horizontally, which means that, hey, this is for sure even function. Okay, that is the first example. Let's try a few more. Second function, fx equal to, let's try trigonometry, cosine x. Cosine x, let's try to plot this. Okay, this should be enough. Now, cosine x should be something like that. And continue to the left-hand side. Okay, I try my best to create a good cosine wave. So here we have, okay, y and x. Here we have y and x. Once again, we consider y-axis to be like a mirror. So we try to figure out whether the left-hand side is like the flipped version of the right-hand side. And as you can see here, if you try to flip the graph on the right-hand side to the other side like that, it's going to look the same thing. So we are looking at the symmetry across y-axis. So once again, this is symmetric across y-axis horizontally. So even for sure. Let's try one more. Okay, let's try something simple. Function x equal to the absolute value of x. Okay, let's try to plot this graph. Okay, something like that. Okay, and we have y-axis and x-axis. And of course, this is going to be a straight line on the right-hand side. Okay, and since we have the absolute value, the left-hand side has to be positive too. So it's going to be something like that. Okay, so this is the graph of absolute value of x. And once again, put a mirror here. And you can see this is definitely a flipped version of the right-hand side. You flip this, and you get the same line on the left-hand side. So once again, this is symmetric, and I can call this one even. So that's how you use observation to determine whether a curve or a function is even or not. Okay, we just perform observation. So what we did over here, this is observation. Now, can we do this mathematically? Can we use equation to check on this property of being even? So let's take a look on this condition right here. So the condition for a function to be even, it must satisfy this equation. It's going to be fx equal to function of minus x. Okay, that is the condition in terms of equation for even function. So you can check on this one too. Okay. So as you can see here, you can see the symmetry inside this condition. This function doesn't really care the sign of your x. It can be positive or it can be negative. In the end, it's going to come out to be the same. So that's why we get the symmetry from the positive side of the x and the negative side of the x. So can we check the property of even by using this equation without plotting the graph? So let's try that. Let's try this on this example. Fx equal to 9 minus x squared. We want to know whether this function right here is even or not. Even, if you can plot this, if you have a plotting calculator, of course you can perform the plotting and you should get something like this. This is 9 minus x squared. It's going to be an upside down parabola with the peak at 9. So it's going to be something like that. And this at the top happens at y equal to 9. That's when x equal to 0. So from the plotting, from observation, this is definitely even. But let's try to use the equation that we have, fx equal to f of minus x, whether we can prove it the other way. Okay, so fx equal to 9 minus x squared. So let's check f of minus x. F of minus x. Now, the input is different. Minus x, so we are going to get something different here. Equal to 9 minus, so here x becomes minus x, so it's going to be this minus x instead of x, and we still have the square. Now in the end we have this 9 minus x squared. Okay, this becomes x squared, becomes positive. Okay, so we have this f of minus x equal to 9 minus x squared. And it turns out to be equal to function of x2. So as you can see, f of minus x equal to f of x. So you have proved that this function is even by using the condition that we have, mathematical condition, even. Okay, so we don't really need to plot in order to determine the property of even or odd. Okay, so that is how you check the even functions. Now let's take a look at the odd functions. This one is going to be a little bit harder. So let's check on this one. Now first of all, let's talk about the shape of the graph. Now let's take a look at this. The condition for the odd function. Shape of the curve. Shape of curve, once again, is mirrored horizontally across y-axis. Mirrored horizontally across y-axis. But not just that, if I stop here, it's going to be the exact same thing as even function. Then mirrored vertically across x-axis. So we are talking about mirrored twice, flipping twice. Flip twice. So here we are going to flip the graph twice in order to check on this condition of odd function. Okay, now what kind of curve is going to satisfy this? So let's take a look here. Let's try maybe just two. Okay, first one, fx equal to x cubed. Is this going to be odd or even? So let's check here. So first of all, I'm going to plot this graph, x cubed. So I'm going to get something like this, y-axis and x-axis. So shape of the graph, the curve, should be similar to the parabola, but this time it's going to go up faster. So it's going to go up faster. Now, on the left-hand side of the y-axis, x is going to be negative. And since we have the power of 3 here, the result should be negative. So, function value is going to be negative over here. And it goes down really fast. Alright? So there you go. We have the graph, the curve of this x cube. Now, we are going to check the symmetry of this curve. So first of all, I'm going to consider this y-axis as a mirror. Alright, and as you can see here, if I consider the flipping just once, I am going to get this, which is not the same as what I have under the x-axis, right? So flipping once doesn't give me what I want down here. I don't have I don't get what I have down here. So flipping one is not enough. So in order to get the curve down here, I have to flip again. So that the second time I need to consider the x-axis as the mirror. And then I flip again. Flip this one, green one up here to down here. And then I'm going to get that blue curve under the x-axis. So this is what I'm talking about. Mirrored twice. First, horizontally across y-axis. Second, mirrored vertically across x-axis. So you flip twice and you get the same graph. Okay? So from this we know that this one is odd from flipping the curve twice, from the positive x to the other side and then down to the negative y and negative x. Now let's try one more. Fx. So we had cosine x before. Now let's try sine x. Equal to sine of x. Okay, let's try to plot this. So we have this y-axis and x-axis. And let's plot sine x. Okay, so it should be something like that. Okay, and the other side, I should have something like this. Okay, and now I try to determine whether this curve is the twice flipping version of the other side. Okay, I want to check whether this curve is odd or not. Okay, so first let's try to flip the right hand side of the y-axis. First of all, I consider this y-axis as a mirror, and I'm going to flip everything to the other side, flipping first time. So flipping first time, I'm going to get something like that. Okay, so flipping first time, I don't get the one that is blue on the left hand side, and I need to flip again vertically across x-axis. This time I consider this x-axis as a mirror, and I flip this blue dotted green, dotted green down here. Okay, and in the same time this is going to get flipped up. So this is the second flip and this is the second flip, and I'm going to get that blue line on the left hand side of the y-axis. Exactly the same thing. So flipping twice, I get what I want. This is definitely odd function, and this comes from observation. The shape of the curve on the left hand side is the twice flipping version of the one on the right hand side, and you have to flip horizontally and then vertically to get that. Okay, observation, that's what we just did. Now, can we use equation instead? This is too much. Do you think maybe you can't flip this in your head? So let's try to use some math terms to check on the odd functions. And for odd functions, it must satisfy this condition. So, function of minus x must be equal to minus function of x. That's all. You need this in order to check the property of being odd. So this one. Okay, what about we try to use this one? What about we use it on this same example? We know that this one is odd. Fx equal to x cubed. Let's try to check on this using this equation whether this f that we have right here satisfy that. Okay, so first of all, let's try to check on the f of minus x. So f of minus x, we are going to get this minus x inside cube. Okay, so in the end we have this minus of x cubed. What about minus of fx? Minus fx is going to be equal to minus of fx right here equal to x cubed. So we have x cubed. And there you go, we have these two to be equal. Minus x cubed, minus x cubed. In the end, we can conclude that in this case, f of minus x equal to minus fx. Therefore, this function is odd. Function is odd. So you don't need to plot. You can use this equation to check on the property. Okay, so we talk about the properties of being even and being odd. Let me tell you one thing. A function can be neither of them. So you make a note right here. A function can be neither even nor odd. Neither even nor odd. Okay, this can happen. Okay, neither even nor odd right here. So that's about all you need to know on the odd and even functions. So let's move on to the next properties of functions, and we are talking about the combinations of multiple functions. So it's going to be about combining smaller functions, subfunctions, to make it bigger. Let's assume that we have two subfunctions here. The first one, fx, equal to square root of x. And the second subfunction, we are going to call it gx. Gx is equal to square root of 4 minus x. And now I'm going to represent these two subfunctions as a transformation. Okay, so here we have this box called function f. And function f is all about taking a square root of something. Alright, something inside, take square root. That is the job of function f. So right here we have this input as x, and it gets fed into this box, and outside it becomes the image of x. F of x is the square root of the input, and here we have square root of x. Okay, now for the subfunction g, it's going to be a little bit different. Subfunction g, okay, its job is to take a square root of 4 minus the input. Okay, its job is to do this. Square root of 4 minus the input, whatever that is. Okay, and right here we have x as the input. X as the input gets fed here, and it becomes the input of the black dot. So in the end, we get this image of x in terms of g. That's equal to the square root of 4 minus the input, which is x. So there you go. That is the transformation. Now we are going to combine them into larger functions. So let's take a look at the first one right here. This first one is a combination of some terms. So let's take a look at the first term we have here. Square root of x. Definitely this one is fx. So looking at this, same thing. Fx equal to square root of x. Now, square root of 4 minus x, the second term. This is definitely g of x. So what we have right here is actually the addition between two subfunctions. Sum of fx plus g of x. Okay, now in terms of representation, you can represent this fx plus gx as one single function. This is going to be equal to, that function is called f plus g of one input value x. Okay, so in terms of the result, it's going to be the same thing, but in terms of the flow, it's a little bit different. So let's take a look here. F plus g is going to be this big black box. This big black box is called f plus g, and its job is to take the square root of the input plus the square root of 4 minus input. Okay, and the input that you feed into this is x. So in the end, it comes out to be equal to square root of x plus square root of 4 minus x, and it's going to be equal to combining these two together, plus you get square root of x plus square root of 4 minus x. But in terms of logic, it's a little bit different. Here we have two separate subfunctions. Here we have just one big function. Okay, but the result is the same. Alright, now let's take a look at the next one. If you understand f plus g, then this one should be easy. This one is minus. So front term, same thing, fx. And second term, same thing, gx. The only difference here is that the operation here is minus. So fx minus gx. Two separate functions. Okay. Now, this is subtraction. Once again, we can combine them into just one big function. And that big function is f minus g of just one input. So in the end, this is like changing this plus to minus, and this to minus, and this to minus. Okay? So same kind of logic, combining two separate functions into big function. Now let's take a look at this one. If you know addition, subtraction, this one should be easy too. Front term, once again, we have f of x, and the back term, g of x. Even though they are combined into one square root, you can separate them. Alright, so separate them, you get this fx times gx, multiplication. And once again, you can combine them using the same notation, f dot g of x. And it's like changing this to multiply, 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 and multiply. Okay, no surprise here. So let's move on to this next one. Okay, as you expect, addition, subtraction, multiplication. Of course, we have division here. So we have the numerator as square root of x. So up here we have fx. And down here, denominator, we have square root of 4 minus x. So this is g of x. So obviously this is fx divided by g of x. And of course, you can change this to f divided by g, one big function, one big box, and one input, which is the same as this, divided by, divided by, divided by, divided by, and divided by. So all of them have the same logic here, combining two subfunctions into big one. Now, the next two is going to be a little bit different. So let's take a look here. First one. First of all, I would like to make a box around what's inside here. Okay, first of all, I would like to take all of this away. I don't need this anymore. Okay, now the first thing I'm going to do here is to put a box around what's inside this square root. Okay, what's inside the square root becomes just a blue box. And inside the blue box, you see square root of 4 minus x. So this blue box is definitely g of x, right? Square root of 4 minus x right here, g of x. Okay, So we know about g, so where is f? Let's take a look here. The most outside function is square root of something. Okay? Square root of something, I have seen that somewhere. Hey, it looks like this. Square root of something. Square root of black dot. So we definitely have a function f right here. So the most outside function is definitely f. So let's make a box right here. The most outside, okay, what about this right here? The most outside function is f, square root of something. Same thing with this one right here. That is the job for subfunction f. But it turns out that this time, that something, the input is not x. It's not the same as this. It's not x like here. It becomes something more complicated. It becomes this blue box. And this blue box is g of x. So this time we have g of x as the input for this f function. Okay? And in order to get g of x, you need to pass x through g. Need to pass x through g. And g is square root of 4 minus something. In order to get this g of x, which is equal to square root of 4 minus x. Alright? And then this square root of 4 minus x becomes this input for this square root of that thing. Alright, so in the end you are going to get the square root of g of x. So we have this square root of g of x, or in other words, this is equal to f of g of x. G of x becomes the input for f. Okay, so let's write it down here. F of g of x. In other words, g of x becomes the input of function f. And once again, we can use another notation. Okay, and this is going to be FOG, composite of functions, with one input. Alright, now let's take a look at the last one right here. Now let's take a look at the box right here. Okay, now I'm going to use green for this one. What about red? Let's take a look at this one as red and think of this as just one chunk. And inside this box it's square root of x, so we know that the inside is fx. Alright, now we don't need this anymore, so I'm going to take this out. Okay, so we have fx somewhere in this last one. What about g? Let's find g. So now I'm going to take a look at the most outside function, and I see this square root of 4 minus something, this red box. Square root of 4 minus something. This looks familiar. It's exactly the same as this. Exactly the same as this. Which means that for the last function, the most outside function, the last example, the most outside function is g. So let's write it down right here. Last one, the most outside function is g, and g has this job, square root of 4 minus the input. But now the input is not x like we had here. This input is more complicated. It becomes fx. So here we have fx as the input for g. And in order to get fx, of course, we need to feed x into this box called f, square root of something. So here we have this fx equal to square root of x. So in the end, we have this square root of 4 minus fx. In other words, we are looking at g of fx. when fx becomes the input of g. So here I can express this as g as the most outside function with fx as its input. And this is going to be equal to composite GOF of x. Once again, when you combine it to this GOF, it becomes one large function. This is one function. Okay? Different from this. This is multiple sub-functions. Multiple sub-functions. And let me tell you one thing. FOG and GOF, different meaning. As you can see here, these two are not equal. Well, there is a chance that they might come out to be equal, but most of the time they are not equal. Different meanings. So keep in mind, FOG and GOF, not interchangeably. You can't just change GOF and FOG like you wish. Okay? You have to follow the order. Okay. Now, that is it about the combination of multiple subfunctions. So all you need to know, addition, subtraction, multiplication, division, and composite. Now let's move to the last topics of today, and that is the manipulation of functions. We are talking about shifting graph here. Okay, so over here it's all about shifting graph. In this course, we are going to work a lot on graphs, and it would be nice if you can play around with the shape of the graph so that you don't get confused about what to do with them, about what to call them. So it's all about having something basic and then you do some complicated things on them, right? Sometimes you have this parabola, but when you know how to shift them, it becomes some other form of shapes that you might see in the future. Alright, so today we are going to shift graph. Now let's use something very simple. I'm going to start with the parabola again. Okay, so start with a parabola y and x, and we have this once again. Okay, this is bad. Let me fix on this one, otherwise I can't go to sleep. Okay, this should look better. Okay, try again. Okay, a little bit better. Now, this is fx equal to x squared, an upside parabola, regular parabola. But now we want to shift this fx a units to the right. So we want to do this, shift to the right a units. But before anything, I would like to say that a is positive and greater than 1. Keep this in mind. A positive and greater than 1. So we are talking about big numbers here. Okay, maybe 1, 2, 3. Definitely not decimals. Okay, so now we want to shift this graph to the right a units, and all you need to do is to do this. F of x minus a. So this is going to become x minus a squared. This new one is going to be the graph of parabola shifted to the right a units. So I'm going to call this f of s, right, new one. So the new graph that we get over here after shifting should look something like this. Shifting to the right a unit. So it should appear at this point. At this point, let's say that this point is a. And you are going to get the exact same parabola. But this time, it's going to touch the x-axis at x equal to a instead of x equal to 0. Before it was at 0, the bottom of the parabola, but now it's at a. So there you go. You know what to do. Put minus a inside the function. Now, what about I want to shift this graph to the left a units? Okay, we did shifting to the right. Now, shifting to the left. So, shifting to the left, all you need to do is to put plus a into your function. X plus a, so it's going to become x plus a squared. And this is going to be the new graph, the new function, shifted one. Fs, let's call this s again, okay? So once again we have this x right here. And the shape should be something like this. Okay, y-axis and x-axis. But now you shift it to the left, a units. So once again you have this parabola. Same shape. But now the bottom part of the parabola is going to be at x equal to minus a. Right here, x equal to minus a. So there you go. To shift your graph to the left, you need to plus a inside your function for the input. And of course, it's going to go into your expression inside the calculation. Now, what about I want to shift my parabola upward, a units? Next thing, I want to shift my graph upward, a units. So, let's take a look here. Alright, should be something like that. So, originally I have this regular parabola. It looks like this one. But now I want to shift it up a units. I want it to look like this. Okay, so this is y and this is x. And it's going to be right here. At this point, y equal to a. Shift it up a unit. What should I do? Okay, so the new function that I need right here is going to be exactly the same as the one I have before, fx, except that the whole graph has to be shifted up a units. So it has to be plus a right here. Plus, okay, what about I do this? Plus a. And here, minus a. Minus a. Plus a. Plus a. So in the end, this becomes equal to fx is x squared plus a. As you can see here, this is the same the old graph, but now you shift it up a units. That's straightforward. What about shifting down a units? So it's the other way around. Okay, I need to draw again. Okay, something like that really quickly. Okay, something like that, x and y, and now parabola shifted down a unit. It's going to look something like that. So the bottom part of this parabola is going to appear when y equal to minus a instead of 0. So right here, y equal to minus a. So the new graph fs is actually the same graph fx, the parabola. But now the whole parabola is going to get shifted down minus a. So minus a. So in the end, we have this x squared minus a. Now you know what to do when it comes to shifting. Right, left, upward, and downward. Now let's move to some other manipulation. What about shrinking vertically? Okay, let's take a look at this one. We have lots of versions here. Okay, shrinking. What does that mean? Shrinking vertically. Let's draw. Okay, to make it clear, I need to draw everything. The original one, parabola. Okay. Okay, so this is fx equal to x squared, and we have y and x. And now we want to shrink this curve vertically by a factor of a. We want to make this shorter, this graph shorter. So it's going to be something like that. Okay. Now we want to do this. Shrink vertically. We want to squeeze it downward. So it's going to be this instead. Shrink vertically. Okay. And it's going to go up. But the same point that used to be over here is going to show up over here. So we shrink this graph vertically. Alright, so in order to do that, we are going to do this. New function. Function of x is going to be, well, the same parabola that we had before, fx, except that everything has to be smaller. Everything has to be smaller, so I'm going to divide. Okay, what about I use blue over here? That should be better. Okay, sorry about that. So fs, new function, shifted, equal to the old parabola, fx divided by a. So now everything is going to be smaller because a is greater than 1. Your function is going to be smaller. Okay, make a note here that all functions values become smaller. All right. Okay. So what about expanding this same parabola vertically? Make it taller. Okay. For this one, make it shorter. And for this version, we are going to make it taller. So it should be something like this. Same point is going to be higher. Alright? So in order to make your parabola taller, you need to do this. New function shifted is going to be equal to the original function parabola of x, but you want to make it bigger, right? So you multiply this with a. Since a is greater than 1, then the whole function value is going to be bigger. Okay, fx becomes larger. Alright? So you know what to do. Expanding vertically, you multiply. Shrinking vertically, you divide right here. Now, what about shrinking horizontally? What is that? Shrinking horizontally, it means that we are going to shrink the original parabola to be thinner. So this time, we are going to make it thinner. Okay? So it's going to be something like this. Make it thinner. Okay, so in order to make this happen, you have to do this. New shifted function is going to be equal to the same parabola function f, but the input should be changed to ax. You are going to multiply this factor a inside. Factor a times x instead of just x like what we have over here. So this extra term a is going to go inside the parenthesis. When it goes inside the parenthesis, it means that x doesn't have to be large in order to get the same function value. So now x can be small, and that's why you get a thinner graph. So you make a note that x value can be small. X can be small to get same function value. Alright, now another version, expand horizontally. Of course, we made it thinner. This time we are going to make it more fat. Okay, more fat. Right? So it should be something like this. It's going to be a parabola that is more fat. Something like that. Alright, I tried my best to make a fat parabola. So this is y-axis and this is x-axis. And in order to get this kind of curve, you have to do this. The function, shifted function, is going to be equal to same f as we had before. But now we are going to perform the factor here. It's going to be x divided by a. Alright. Divided by a. And as you know, a is greater than 1. It means that in order to get the same function value, x has to be larger, and that's why everything gets expanded outside. X has to be larger. In this case, x can be smaller. Okay? So, once again, keep in mind that a is greater than 1. Very important. So, here x needs to be large to get same function value, fx value. And that's why you get a parabola that is expanding horizontally. Alright, now let's move to this last slide. Okay, so the last two manipulations, it's going to be about reflecting your graph over x-axis and y-axis. So here, I think the parabola might not be a good choice, so I'm going to change it into something else. So let's do this. What about this? Okay. Okay, so what about I try to use square root of x? So let's use that. Square root of x is going to be something like this. Square root of x. Okay, so we have fx right here equal to square root of x. And now we want to try to reflect this over the x-axis. So we want to reflect this over this thing, this axis right here. So we have this y-axis over here and x-axis over here. Now, in order to reflect a graph over the x-axis, you basically change the function value to be the opposite sign, right? Change sign of function value. So you want to flip and you want to make it looking like this. So in the end, you are going to, okay, so what about I give you the expression for the shifted version. The shifted version should be fs, okay? And since we want to change the sign of everything, what used to be positive, function value positive, will become negative value. So it's going to be this, minus fx. So what used to be up here, is going to get flipped across, well, over the x-axis and showing over here. So that's how you do it, flipping your graph over the x-axis. All you need to do is to put minus sign in front of your original function, and everything is going to change the sign. Now for the last manipulation, we want to reflect our graph over y-axis. This is going to be a little bit different from what we did earlier. So the last one, we flip it over the x-axis, so we flip it down. But now it's going to be on y-axis. It means that we are going to flip it horizontally on the side. So let's take a look here. I'm going to use the same function. So starting with y-axis and x-axis. And I also have the same function, fx equal to square root of x. Fx equal to square root of x. And here I have y-axis and x-axis. Now I want to reflect this graph over the y-axis. It means that the y-axis becomes a mirror here. Okay, we have a mirror on y-axis, and we flip it, reflect it, and we should get something like that. Flipped version of the blue graph. Okay, so that's what we want. Now let's take a look at the expression in terms of math, what we need to do. To get the shifted graph on the other side of the y-axis, f shifted, same input x, it's going to be equal to, well, the same function. Oh, I'm sorry about that. Same function except that we have minus sign in front of the x input of your function. So that is it. The only difference is here. Oh, once again, right here, let's change the color, the difference. And here, minus over here. Why do we put minus sign over the in front of x in this case? It's because, look at this. Originally, we have this graph, square root of x, and along this graph, along this curve, x is positive all the way through. But once you flip this graph, it's going to be on the other side, and on the other side, the sign is changed. It's the opposite. And that's why you need to put minus sign over here to change everything that used to be positive to be negative. And in the end, you are going to get this flipped version of the square root of x. Okay, so that's how you flip a graph over y-axis, or flipping horizontally.